Hi, in the last session, we had some overview of how we define the signals in VSGL. Now, in this video, we will talk about the data types which are pre-supported by VSGL. We will understand what type of information those data type carries in the signals. This is important because you can only connect one signal to the another signal when their data type is same. If you attempt to assign a signal of one data type to the another signal of a different data types, the VSDL compiler will flag an error. This strict type checking helps maintaining the consistency and avoid the unexpected behavior in your designs. In VSDL, the assignment statement is not represented by the equal sign as in C or C++. Instead, it is less than sign followed by the equal sign, which serves as the VSDL assignment operator as highlighted in the red. This operator resembles like an arrow which is indicating the direction of the data flow. Like for example here in the expression signal underscore A gets the value of signal underscore B semicolon. Here the value of signal B will be assigned to the signal A. So now we know the syntax of the signal assignment. One of the most common signal type in VSDL is std underscore logic, which is similar to a wire as it can carry a logical 0 or logical 1, representing a single bit of the data. The std underscore logic data type is declared in the std underscore logic underscore 1164 VSDL package. So to use this data type, you need to declare the std underscore logic underscore 1164 package in your VSDL code. A single bit represented by either logical 0 or logical 1. You can think of it as a single light switch that can be on or off, like 1 or 0, to use this data type. So these are the most common values of the digital systems. But the std underscore logic offers more than just the binary values like 0 and 1. It can also represent a high impedance state denoted by Z. This is like a neutral state where the signals isn't actively driving a 0 or 1. You can imagine a wire that is disconnected from its source. However, using the tri-state signals require more cautions. While they are useful for external input-output pins that can be disconnected and controlled by the other circuits, most internal signals within the FPGA cannot be tri-stated. You are only allowed to tri-state the signals that directly drive to the I/O pins of the FPGA. This is because only the I/O pins having the tri-state buffers, while all the internal signals in the FPGA do not have the tri-state buffers in hardware. Therefore, you cannot drive the internal signals in the FPGA to the tri-state. Beyond the digital values like basic zeros and one values and the Z state, which we just discussed, we have more states in std underscore logic. We have H and L state indicating the weakly driven high or low states respectively. Imagine a wire with a weakly pull up or the pull down resistors, influencing its voltage but allowing a stronger driver to override it. Similar to the tri-state and weakly driven signals, W represents a weakly driving signal with the unknown value. This can occur during the simulations if the signal's true strength is unclear. The U state signifies an uninitialized value, which is a reminder to properly initialize your signals in your FPGA code. Now things get interesting with the X state. This arises when two conflicting drivers try to assign the different values like 0 and 1 to the same signals simultaneously. Then the simulator keeps this in the confusion, marking the value as unknown, means X state. To avoid this, you need to ensure that your designs has the clear ownership of each signal to prevent such conflicts. Finally, the dash, that is don't care state, allows the design synthesizer some creative freedom. It can choose to assign any value from 0 and 1. In this state, to optimize the circuit for the speed and area, resource usage, it is important to remember that these extended states like W, U, X, dash, H, and L are primarily for simulation purposes. While they can help the model in the real world scenarios like pull up registers or pull down registers, they cannot be directly implemented in the FPGA hardware. For example, the H state or the L state can be used to simulate the pull-up registers or the pull-down registers. and some of the other states are used to indicate the undefined signals or the uninitialized signals only in the simulation state. We will go deeper into the FPGA implementation details in the later part of this course. But remember that the code that can be synthesized must always use logical 0 or logical 1 or try state. All the other states mentioned in the std_logic can only be used for the simulation process only. std_logic signals are widely used and you will also use it often in your VSDL designs. You will encounter that the std_logic signals when connecting the logical gates, which are the basic building blocks of a digital circuit. Similarly, they can be used to connect the flip-flops which store the data bits. Even clock signals and reset signals, which control the timing and the initialization of your designs. And they rely on the std_logic signal for their 0 and 1 logical labels. Now let's explore that how to declare the std_logic signals in VSDL code. The first example showcases a basic declaration. It is similar to that how you might the label a wire in a circuit diagram. The second example demonstrates the initialization, where you assign an initial value, like 0 in this case, to the signal during the declaration. This is helpful for setting up your design to a known state from the start. Finally, the last example which shows the signal assignment, where the value of signal B is assigned to the signal A. Think of it, you are copying the information from one wire to the another wire. But make sure that both the signals are of same data types as we talked earlier. Let's have a quick example where you can use the std_logic signal type. So take a look at this example featuring an inverter and a D-type flip-flop. They are connected seamlessly using two std_logic signals, SIG1 and SIG2. Imagine that SIG1 as a wire carrying the data from the inverter's output to the flip-flop's input, and SIG2 acts as a bridge between the flip-flop output and the inverter's output. Just like wires in the traditional circuit, these signals facilitate the communication between the components. Furthermore, the clock signal CLK connected to the flip-flop is also an std_logic signal here, because the clock signals typically toggle between 0 and 1 to control the timing of the operations within your designs. By understanding that how the signals connect and interact with the logical elements like flip-flops and respond to the clock signals, you are laying a solid foundation for the mastering the VSGL designs. Think of these signals as the communication channels that allow the logical elements to exchange the data and perform their operations. This is the fundamental concept in building the digital circuits in VSDL. Now that we are comfortable with the single bits, VSDL introduced the std_logic_vector data types for handling the multiple bits together. Imagine a bunch of wires grouped into a single cable. That is the essence of a vector. An std_logic_vector acts like an array of vector of individual std_logic signals. In simple terms, it is the group of bits traveling as a unit, similar to a multi-lane highway carrying the multiple data streams simultaneously. Just like the std_logic, it requires including the std_logic_1164 package for proper use in the VSDL code. Get ready to explore how to declare and use the std_logic_vectors to represent more complex data in your FPGA designs. So, the std_logic_vector data type empowers you to handle the collection of bits for the std_logic signal types. Imagine a data bus or an address bus in a computer. They carry the multiple data lines simultaneously, like 8-bit, 16-bit, etc. An std_logic_vector is just like that. An array of vector of std_logic signals bundled together. This make it perfect for representing multiple data like registers, counters, and timers within your FPGA designs. Declaring std_logic_vector is similar to declaring a single bit std_logic signal, but with just a small twist. Since it is an array, so you need to specify the number of bits in the vector using a range, and the keyword down to gets used for it. Here we see two examples, an 8-bit signal named as A and another 8-bit signal named as B. The second signal B is initialized with the hexadecimal value A1. Notice the value inside the double quotes. The bottom of the slide highlights the bit ordering, where index 7 represents the most significant bit MSB and index 0 represents the least significant bit LSB. Assignments with the std_logic_ vectors are slightly more complex, so we will understand its assignments with some examples. Assigning values to the std_logic_vector signals is straightforward when dealing with the signals of the same size. So if you look over the example where I am assigning signal A to signal B using the assignment operator, then this will work perfectly fine because both the signals are std_logic_vector type and having the same length, which is 8 bits. The second row of the table demonstrates the vector slice assignment. Imagine a scenario where you only want to copy the specific lane, a bit here, from the vector type signal to the another vector type of signal. Like here, bit 3 and 2 from the signal B are assigned to the bit 6 and 7 of signal A. This is also allowed in VSDL because the number of bits are same between them, which is 2 from signal A and 2 from signal B. This targeted assignment lets you manipulate the specific portion of your multi-bit data within your FPGA designs. Now continuing to the vector slice assignment, the third row showcases the assigning a single bit. Like here, bit 0 from signal B is assigned to the bit 4 of signal A. This allows you to insert a single data bit into a specific location within your multi-bit signal. In the fourth row, we assign bit number 6 of signal A to the logical signal C. So in short, VSDL offers the powerful features called array attributes, which come in handy when working with std_logic_vector signals, essentially the array of bits. These attributes provide the value information about the vector's structure. The left attribute tells you the index of the leftmost bit of the vector, while the right attribute reveals the rightmost bit of the vector. Similarly, the total lengths tell you the total number of bits in the vector. By using these attributes, you can write more readable and adaptable VSDL codes. In the next session, we will be talking about the attributes of vector type signals and how you can use them for clean and generalized VSDL codes. So stay tuned for the updates. If you did not subscribe till now, then please do subscribe to learn and grow community for the regular updates. If this video is informative, then please like this video, comment on video, and don't forget to share. Thank you for watching.